Nebulous means?
The cloud? What?
The thing too.
Isn't it a pip cloud?
A nebula is like a nebula is an astronomy term where you have like it's kind of like a cloud of stars. It's a
after a star.
but nebulous means that it doesn't have a clear definition. It's vague or fuzzy. Nebulous. That's a good SAT word, nebulous. Yeah.
They got rid of all the hard vocab in SAT, so we got dumbed down.
Yes.
That's good.
Is that right?
Yeah.
And
They
now we
changed
just have
it.
wave.
They changed it so now the score is 1600, and all the hard vocab from the SAT reading is now gone.
I didn't know that.
So we don't have to study vocab.
All right. So anyway, speaking of nebulous, can we come up with a chemical equation for this reaction? What are they even talking about here? We need to write a chemical equation so we can figure out Q?
Yes.
Well, all right then. When you see the term standard hydrogen electrode, does that mean anything to you?
No. It means standard hydrogen electrode.
You know how we have this baseline half reaction where the hydrogen ion gains 2 electrons and becomes H2? I call it baseline because it has a voltage of 0. That is the standard hydrogen electrode. So for these 3 words, what they're talking about is this. Somehow, the authors of our book expect you to just know that. Because when you look at the solution guide to this problem, it'll just say, well, use that. With no explanation.
No, I think it probably is in the textbook somewhere.
Yeah,
They say that it's a standard hydrogen.
You're supposed to know it.
It is.
You're giving them a lot of credit.
Well, but you're always giving
Now, I do want to warn you. There is another place in the reduction potential table that has another hydrogen. It's another form of hydrogen. It's the H- hydride ion. It's far down on the right column. See if you can find it. It's hydrogen gas reducing to hydride.
Yeah.
See it?
That's what I thought it was.
And look at that potential. That's a very good oxidizing agent, or oxidizer, is the hydride ion. When you turn it around, it has a nice big positive number. However, it is not common. Hydride ion doesn't show up very much. It's hard to make. If you could find it for your battery lab, you'd be in pretty good shape because it's a very good oxidizing thing, but you won't find it. So this is a standard hydrogen. This is very common, and that's what we would use for hydrogen. Now, in the same regard, we have a copper metal electrode. That gives away what is the other thing. Now, I don't know whether hydrogen is the anode or the cathode. It's written up here as a reduction. So does that necessarily mean it's the cathode? No. We have to figure out what both of them are.
Or what?
I'm watching you, and you're watching something else, and I'm in the dark about it. Okay, so anyway, the copper metal electrode, we need to figure out what that one is. Now, on your reduction potential table, there's copper plus 1 and there's copper plus 2. How do you know which of those two you're going to use?
You're gonna use the ones that says.
Oh, yes, right here. It's copper. And I was going to say that for copper, they didn't even tell me that during 5th hour. They just looked like, huh? Hopefully nobody's watching that at 5th hour. But copper plus 2 is way more common than copper plus 1. So if you're ever given copper and you don't know for sure which copper ion it goes to, plan on it going to copper 2, because it's a lot more common. So we're going to use this half reaction for the copper metal electrode. All right, well, let's see. We need to take these two. Both of them are written as reductions, so one of them has to turn around. How do you know which one to turn around? The two added together have to be positive. One of them as an oxidation and the other one as a reduction have to add together to give a positive number. So when we look at these two, this reaction has a a reduction potential of positive 0.34.
If you flip the hydrogen one, won't it still be 0?
Yes. Yeah. Or as Alan would say, negative 0. This has a reduction potential of 0. Right. So is it obvious that we're going to turn the hydrogen one around?
Yes.
So then when we add the two together, it's a positive cell potential. That's what we do. Turn that one around. So we have copper plus 2. Then this one, remember, gets turned around, so it's H2 as a reactant. Yields copper metal plus 2 H pluses. What's our N value in this problem? N. From the Nernst equation, it's 2. Right. 2 electrons given off in our oxidation, 2 electrons taken in our reduction. Now this thing has a standard cell potential of positive 0.34 volts. Because we have 0.34 plus the 0 gives us a cell potential of 0.34. Yeah? Now, are we in good shape to do the problem?
Yes.
I think so. This is not in standard conditions. Oh. It says that our copper ion concentration is 2.5 times 10 to the negative 4th mole. It doesn't give us a concentration of hydrogen. It doesn't give us a pressure of hydrogen gas. Can we make any assumptions? Actually, we can't. We're not even assuming. We know what the pressure is of that and the concentration is of that. From what in the problem?
25 Celsius.
Well, 25 Celsius, Nabil, the word standard. See how it says a standard hydrogen electrode? That means that we're at standard conditions in that hydrogen compartment. So that means we have 1 molarity of that. And remember, gases are included in our equilibrium, Q's and K's. So the hydrogen gas is 1 atmosphere. That's a gas. Now the copper we don't care about because it's a metal, a solid. Solids and liquids, they don't ever go into Q's or K's, but aqueous and gases do. Now this is going to be strange. I believe this is the first time in this course that we'll see a two-phase reaction in which we're going to need a Q that has both molarity and atmospheres in it. But as long as you're in molarity for aqueous things and in atmospheres for gases, you can combine the two. And put them both into the Q, which makes me squirm a little bit, but it's right. So let's use the Nernst equation. We have cell potential equals the standard cell potential, which we know, 0.34 volts minus 0.0591 over N. We know N is 2. Yeah? And then times the log of Q. This is where we'll put the products over the reactants. Do keep in mind the hydrogen over here has a 2 coefficient. It's 1 molarity, so you're going to wind up squaring 1. It doesn't really matter if you forget it this time, but next time it might matter if it's not 1 for the concentration. So just be aware of it. It's 1 squared on top, and on the bottom we have 2.5, not just 2.5, sorry, times 10 to the negative 4th. And then 1 atmosphere down there with it. I'm not even going to put units on because it makes me squirm, like I say. Because that would be molarity and that would be atmospheres, and it just doesn't seem right. But it is right. When you do that, when you have like a two-phase reaction, concentration of solutions and a gas bubbling in, your pressure unit must be atmospheres in order to plug that number in for Q. Don't call it 760 torr or whatever. It's got to be in atmospheres. Yeah.
How do you know the C plus 2 is aqueous, but the C is a solid?
Oh, because you can't have a solid, you can't have any physical state for an ion except for aqueous.
Okay.
Yeah, for dispersed forms of matter, charge, that gives away that it's aqueous. Yep. And then Cu has to be a solid, because copper with no charge would be elemental copper, which in its physical state is solid. Oh, that was Shuzani, right?
Everyone's leaving you.
Was that you that just said that, Jane?
Yeah.
Oh.
Video evidence. Roll tape back.
Doesn't even show my face.
Okay, so we get an answer. Oh, I have erased part of this. This was 0.34, and then minus that. That's what it
The marker has betrayed you.
is. Anybody feel like calculating? 0.23. Thank you. 0.23 volts. So this one has changed by a lot. Not really changed, but this has not like gone on, and that's kind of what it landed at. This is a reaction who's starting with a copper concentration that's very low. So this reaction really is product heavy because the concentration of the reactant is so low. So we're going to have a small cell potential. Another thing that I wanted to mention about this, if I asked you to sketch this cell, where it says a standard hydrogen electrode, the copper electrode is not a big deal. You're going to have a bar of copper in a solution of copper ions, like copper sulfate. But the standard hydrogen electrode is going to look like this. Now I want you to pay attention to this. I'll put it over here next to the board for Elena. We're going to have the hydrogen ion, like normal, and that's going to be at 1 molarity. We'll have to have a platinum bar in here, because we have to have a metal inserted in there so the electrons can come in. And also, this is different, we're going to have a tube that, you know, maybe would be connected to some vat that has hydrogen in it, H2 gas. Sorry, I'm going behind the TV for some of you. But anyway, there's hydrogen gas that's being bubbled in at a pressure of 1 atm. And so you would have to show this source of hydrogen gas bringing the bubbles in. You're bubbling in hydrogen gas at a pressure of 1 atmosphere. That was really not nice of me to do. I'm sorry. You can get up and move if you want to look at it. Or I'll leave it up there. But yeah, when you draw a standard hydrogen electrode, I need to see the hydrogen ion at 1 molarity and the hydrogen gas coming in at 1 atmosphere. That shows that it's a standard electrode. And you'll see in the solution guide, when it has a gas that's present, they're bubbling the gas in with some tube going into the beaker. It's fine.
How the cell, the picture of the cell would look like.
This is just the hydrogen ion, which is the, that would be the oxidation. So this would be the anode. Okay. And you'd still have a salt bridge. I didn't even draw the salt bridge to it. This is just the anode compartment. Okay? Anything else, Matt?
What is the hydrogen like doing? Like the hydrogen gas? What is that doing coming in? What is it?
This is kind of weird, isn't it?
Yeah.
We would, we're concerned about the hydrogen that's in this solution. So this is an anode. We know that because the copper reducing had a positive 0.34 reduction potential. So that means that, remember, got turned around. So hydrogen gas, when you have this circuit running, the hydrogen gas is going to migrate over to the platinum wire. The bubbles are, literally the bubbles will move and shift over toward this, and they will kind of get changed or transformed as they give off electrons, and the electrons flow through the platinum and up through the wire. Remember, this is an anode, so the electrons are leaving, going into wherever the cathode is. So these bubbles really aren't just going up and out. They'll bubble over here, and they'll be on the platinum bar at a pressure of 1 atmosphere. Now, if we wanted the reaction to go faster, one of the things that we might be able to do is put a lid on this container and pressurize it and make the hydrogen concentration greater. That would help it to go faster.
You